Welcome to The Explainer. So today we're stepping into the surprisingly high-stakes, intensely complex world of water utilities. We all just turn on the tap and expect clean water to flow, right? But behind that simple, everyday action is a massive infrastructure network battling some pretty unprecedented modern environmental threats. Today, we're going to look specifically at how the SASB standard framework measures the resilience of these critical water supply systems against everything from severe scarcity to climate change.
It really comes down to this one core question. How do we protect our most vital resource from an unpredictable climate? The challenges of managing water supply systems today are absolutely immense. Utilities aren't just dealing with old, leaky pipes anymore. They're literally on the front lines of a rapidly shifting global environment, and they're tasked with ensuring that millions of homes, businesses, and essential services just don't run dry. No pressure, right?
Okay, let's dive into this. Here's our roadmap for today. First, the water supply threat. Second, measuring baseline water stress. 3, risks, scarcity and contamination. 4, strategies for mitigation. And finally, number 5, adapting to climate change.
All right, Section 1, the water supply threat, major vulnerabilities.
Before we can even start to measure resilience, we really have to understand the sheer scale of the vulnerabilities here. The SASB standards highlight how these compounding threats just stack up. We've got water scarcity and source contamination right at the top of the list. But then, add to that the looming risk of catastrophic infrastructure failures, sudden regulatory restrictions, and competing users all basically vying for the exact same limited resource. When you combine overconsumption by us, the customers, with climate change-induced droughts, well, you get a perfect storm. It's a storm that can severely impact a utility's revenue, its day-to-day operations, and honestly, its fundamental ability to serve the community. Moving right along to Section 2, measuring baseline water stress. Exposure to risk. So how does the industry actually quantify this vulnerability? Identifying stress regions is the absolute first vital step in measuring a utility's risk exposure. The SASB standard relies on classifications defined by the World Resources Institute's Water Risk Atlas tool. They're looking specifically at regions categorized as having high or extremely high baseline water stress. Basically, if a utility is sourcing its water from these red zone areas, its operational risk profile just goes completely through the roof. And when we talk about sourcing water, we have to be incredibly precise about what actually qualifies as usable fresh water. According to the standard, if there's no local legal definition, fresh water is strictly defined as having less than 1,000 parts per million of dissolved solids. 1,000! That tiny number really drives home how precise the measurement and chemistry of this resource actually has to be. Just a slight increase in dissolved solids can render a primary water source completely unusable unless you use super expensive, really energy-intensive treatments. And this brilliantly illustrates the next layer of risk. Under metric IF W440A.1, utilities must report not just the total amount of fresh water they source from those highly stressed regions, but specifically the percentage they have to purchase from a third party. Why does that matter? Well, think about it. If you're relying heavily on third-party wholesale water purchases in a region that's already experiencing extreme drought, your supply chain is incredibly fragile. You are wide open to massive price spikes or even sudden supply cuts. It's a really risky position to be in.
Next up, Section 3, risks, scarcity and contamination, day-to-day threats.
Let's shift our focus to the specific day-to-day realities these utilities have to navigate. Imagine trying to manage a massive infrastructure grid under highly unpredictable conditions. Utilities face severe environmental constraints. We're talking deep droughts, wild interannual or seasonal variability, and extreme severe weather events. And on top of the sheer scarcity of water, they also face the constant risk of the sources they actually do have becoming contaminated. It is a massive, never-ending balancing act between having enough water and ensuring that the water you have is genuinely safe to drink. Now, one major response to all this scarcity is technological improvement, specifically water recycling. It's a total game changer. But, all recycled water isn't treated equally. Utilities actually report on two distinct streams. First, there's potable reuse, which means treating wastewater until it's safe enough to directly or indirectly augment the actual drinking water supply. Then you have non-potable reuse. This is water treated for recreational landscapes, agricultural irrigation, or industrial processes. Diverting recycled water to industrial users is a fantastic technological strategy because it saves the really precious potable water for human consumption. But contamination still remains a huge hurdle. Let's look at this list of contaminants of emerging concern that are highlighted in the standards, drawing straight from World Health Organization guidelines. We're talking about pharmaceutical residues, personal care products, flame retardants, detergents, and endocrine disruptors. All this stuff is making its way from our households and industries directly into our water. Dealing with these often unregulated contaminants is a massive public health and financial risk factor. I mean, if a utility can't treat these through advanced technologies, they face severe regulatory fines and, honestly, a total loss of community trust.
Okay, moving to Section 4, Strategies for Mitigation, Securing Our Supply.
We know the threats, so how do we fight back? Well, there's a 3-tier strategic hierarchy that acts as the real backbone of a utility's defense. Step 1 is the diversification of water sources. Basically, don't put all your water in one basket. You mix surface water, groundwater, and recycled water. Step 2 is intense contingency planning for critical infrastructure failure. If an earthquake takes out a major aqueduct, what is the exact backup plan? And Step 3 relies on alternative watershed-based approaches. This means aligning the utility's infrastructure decisions with the broader ecological health and goals of the entire watershed basin. It's really about looking at the big picture.
Finally, Section 5, Adapting to Climate Change, Infrastructure Shifts. Now, resuming in on how macroeconomic climate shifts directly challenge the physical pipes and plants of our utility networks. Climate change acts as a massive threat multiplier. The SASB standards actually require utilities to assess the specific threats to their physical infrastructure from climate-driven events. Rising sea levels can inundate coastal facilities with saltwater. Increasing storm intensity can completely overwhelm wastewater treatment plants, causing untreated sewage to spill. An extreme drought? It doesn't just mean less water. The shifting, drying soil can actually cause underground water mains to literally crack and fail, leading to sudden, unplanned service disruptions. Because of these increasingly intense storms, utilities have to track a very specific metric: their wastewater treatment capacity located within 100-year flood zones. Now, a 100-year flood zone is defined as a land area subject to a 1% or greater chance of flooding in any given year. Think coastal floodplains or low-lying ponding areas. If a utility has a massive portion of its treatment capacity sitting right in a high-risk flood zone, a single severe weather event could easily knock out sanitation for an entire city. Not good. So the crucial point here is that all of this climate theory ultimately culminates in hard, auditable data. Under this SASB framework, utilities must meticulously track metrics regarding network resiliency and impacts of climate change. This includes counting the exact number and volume of sanitary sewer overflows, determining the percentage of that volume they managed to recover, and tracking every single unplanned service disruption, plus the exact number of customers affected by it. This data forces transparency. It shows exactly how resilient a system really is when nature pushes back. Which leaves us with this final thought. We've seen the serious threats of water scarcity, source contamination, and climate change-induced droughts. And we've seen how mitigation requires diverse supply sourcing, advanced technological treatments, and really robust alternative watershed planning. So considering these ever-evolving threats of tomorrow, how resilient is your local water utility? Are they really prepared for the next 100-year flood or the next historic drought? It's a question definitely worth investigating in your own community. Thanks for joining me on this explainer, and keep asking the right questions.